Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD transfer through a metal molding process. So this is a very simple model, and for understanding the model, let us have a segmented view of this model. We can cut it from front plane. This is actually a simple bucket, and let us view it from front plane. We have got runner and riser, and through this inlet opening will provide molten metal at a higher temperature. It will pass through this cavity, and surrounding this cavity we are having sand mold. And in this analysis we'll try to see the pressure and temperature distribution through the different sections of this metal, and by the same time we'll see the pressure and temperature through different heights using XY plots. By the same time we'll see flow of molten metal. Initially the cavity will be filled up with air, and we'll analyze this one using SolidWorks free surface technique. Okay, this is a closed geometry. We have provided leads at this opening and two other entries, that is the runner and this is riser, right? So without wasting time, let us start our analysis. First of all, we need to start from flow simulation, and for initiation of flow simulation environment we need to start with wizard itself, and we are keeping the name of the project as project 2. Next to that we need to select unit systems, and we are considering default unit system as SI, and temperature we'll consider as degrees Celsius. Next to that we need to select analysis type. It will be definitely an internal analysis. And from physical features we need to select fluid flow. As it is a free surface technique, it will be a transient analysis. It will be dependent on time. In this case we are considering total analysis time as 4 seconds, and output time step we are considering as 0.1 second. That means after each 0.1 second result will be saved, and definitely gravity is involved in this case, and the direction of gravity will be y as indicated by this green arrow. So along y it will be minus 9.81 meter per second square, and along z it will be 0. And it is a free surface technique, as inside this cavity it will be filled up with air. So we are considering this one as free surface technique. Next to that we need to select different fluids. It is composed of two fluids. One will be air and another will be molten metal. In this case we are considering molten aluminum at a temperature of 800 degrees centigrade. So initially the gas will be air, and from liquid we are considering user defined liquid as liquid aluminum. We have created this property. Let us select that one. So we're considering two fluids. One is liquid aluminum and another is air. It is showing that default fluid type is immiscible mixture. Next to that we need to select materials, and in this case material it will be composed of molding sand. That is also user defined. We have provided specific properties of molding sand. Next to that default outer wall thermal conditions and roughness we are considering, and finally from thermodynamic parameters pressure will be 10135 pascal, and temperature we are considering as 20 degrees centigrade, and concentration it will be initially filled up with air, and solid parameters it will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. Let us hide this domain and we can apply our boundary conditions. For applying boundary conditions, let us have a segmented view of this model. So we can cut it from front end and apply our boundary conditions. We need not consider fluid subdomain because we are having single fluid domain, and initially this fluid domain will be filled up with air, and we have to pour molten metal from this runner. Solid materials have already been defined. It is made up of molding sand. So we need to start from boundary conditions. Insert boundary conditions, and we need to provide molten metal from runner at a specific velocity. Let us select inlet velocity as 0.1 meter per second, and from thermodynamic parameters we need to select temperature as 800 degrees centigrade. And substance concentration also we need to see, and it will be made up of aluminum, so we can replace air by liquid aluminum. Grain check, and we need to select the specific location from which we need to provide this aluminum. We need to provide this molten aluminum, that location to be selected. Grain check. Now two more boundary conditions are needed. That means the exit of this one will be having atmospheric pressure, but at the same time the end of the cavity also filled up with a lid. So at these two openings we need to provide atmospheric conditions. So again, insert boundary condition, and it will be atmospheric pressure at the two exit locations. Let us select that exit of this bucket. Selected. Grain check, and another boundary condition is needed, that means the exit of this riser. So insert boundary conditions, and it will be atmospheric pressure or environmental pressure at the exit of this riser. Let us select that location, that is lead number 5. Selected. Grain check. So all the boundary conditions we have applied. Next to that we need to select goals. For goals we can select surface temperatures at different locations, right? So it will be the inside of this cavity and outside also. Let us select the different goals. All will be surface goals, so insert surface goals, and it will be average temperature of fluid at the inlet of this cavity. First one is selected. Grain check. We can rename this one as average temperature of fluid at inner conical surface. Done. And to select that outer conical surface we need to hide the outer mold cavity. So let us select the complete model, and we can hide that outer cavity. Done. So next goal will be surface temperature at the outside of this cavity. So goals, insert surface goals, and it will be average temperature of fluid at the outside surface of this conical surface. Done. Grain check, and we can rename this one as average temperature of fluid at outer conical surface. We need to select two more goals, that means the average temperature of fluid at the outer cylindrical surface, and by the same time we need to find out average temperature at the exit of this riser also. So we need to go back to the model again, and let us unhide this one. We got the previous model again. Now two more goals are needed, so I can select it from the goals. It will be insert surface goals, and we need to find average temperature of fluid at the outside cylindrical surface. Done. Grain check, and we can rename this one as average temperature of fluid at outer cylindrical surface. Done. Finally, another boundary condition is needed. That means average temperature fluid at the exit of riser. So we can cut the model again from front plane and we can select that specific location of the riser. So let us make it big for selection of this one, and we need to select the last goal from here, insert surface goals, and it will be average temperature fluid at the exit of riser. Selected, green check, and we can rename this one as average temperature fluid at riser exit. Done. All the goals are defined. Next to that, we can go for finite mesh. So insert local mesh, and you can refine up to level 3. Let us select the specific locations where we want to have refined meshing. Done. Green check. If running this simulation, we need to do another thing. That means from solve, we need to select calculation control options, and from settings, we need to select periodic, and you can select different parameters like immiscible air, immiscible liquid aluminum, mass fraction of air, mass fraction of liquid, etc. You can select. So okay, done. Now we can run this, but we have already done this one in project 1 with the same data, so we can view our results from project 1. Let us load the results from here. Results loaded. First of all, we need to make the Transient Explorer on. That means we can see different temperature distribution, pressure distribution, etc. at different times. So from results, let us introduce Transient Explorer. First of all, we'll see cut plots of temperature from front plane. So insert cut plots. It will be temperature fluid from front plane. Green check. This is the temperature distribution. As we told that from this runner, we have provided molten aluminum at a temperature of 800 degrees centigrade for 4 seconds. It is not a steady state condition, it is a transient analysis. So let us view how this temperature distribution is occurring inside this one from Transient Explorer. At different times, you can see how molten metal is flowing through this mold cavity. At different times, you can check it. As time is approaching, the mold cavity is filled up with molten metal and temperature is also increasing. Right? Now instead of this temperature distribution, let us see pressure distribution also. With pressure, green check. You can see pressure at the entry is less, but throughout the other portion, pressure is high. And at the bottom portion, pressure is very, very high. And different times you can see pressure distribution through this mold cavity. So maximum pressure is at the bottom portion. So let us close it and we will see velocity distribution through this mold cavity. It is not symmetric one. So when we are supplying molten material from the runner, that portion is having higher velocity, and in the right hand side, in the riser portion, velocity is not that much of high because it is acting against gravity in the right hand side, and in the left hand side it is acting towards gravity, right? Excluding that one, we can see some other parameters like mass fraction of molten material also that can be viewed. Let us see. It is composed of two different fluids. One is molten aluminum and another is air. So that can be viewed properly. So it will be mass fraction of liquid aluminum. First one we can see. So you can see some part is filled up with air also. It is not completely filled up. So we have provided only 4 seconds. Up to 4 seconds you can see molten metal is coming up to this opening. It's not rising up to that runner position. So we need to provide more time for that one, right? It is not a steady state condition. Let us close it, and next to that we will see some other thing, that is sloshing effect also. You can see because inside this one it was filled up with air, and from this runner position we have provided molten aluminum at a temperature of 800 degrees centigrade. So when it will be falling under this cavity, it will be having some kind of sloshing effect inside this air cavity. Let us see that one. This immiscible aluminum, you can see it, immiscible aluminum. So some kind of sloshing effect will be there that can be viewed here. Let us make the color black for better understanding, right? So that plot to edit definition, and we want to see immiscible liquid aluminum. Let us consider the color as black for better viewing. Grain check. Let us see the sloshing effect of liquid aluminum inside this cavity. Let us close it and clear and hide this one. You can see some other things like surface plots also. That means throughout this surface what will be the temperature distribution, pressure distribution also that can be viewed. Let us see surface plots. Insert, it will be at the boundaries only. You can use all phases. It will be temperature of liquid aluminum. Green check. It is actually the representation of 3D. Actually it is showing the surface. Let us rotate this one to see in a better way. You can see the temperature distribution through this conical surface, right? And you can play this through this Transient Explorer also. You can see how the conical bucket is filled up, and actually the blue portion is filled up with air particles. It is not actually solid one. It is showing the boundaries only. It is showing the surfaces. Right? Let us close it. Clear and hide. Next one is very important part, that is XY plot. Through these different heights, or you can say along this inclined height also, you can see temperature distribution at any location. Let us see the front plane. Now I want to view this XY plot. Insert XY plot, and we need to select the specific line. Line can be viewed from here. We have got two lines. Let us see first this vertical height, and we're going to see parameters like pressure and temperature. Let us see temperature of fluid and pressure. But at the same time, we can see some other parameters like velocity also, and mass fraction of liquid aluminum, etc. We can see, right? And that can be exported to Excel, or you can view it from here itself. Let us export this to Excel to analyze this one in a better way, right? So we can select all these parameters also, but our concern is about to see the temperature distribution and pressure distribution. Together with that, we can see velocity also. Let us export it to Excel and see it in a better way. So the bucket is actually 0.5 meter. We can see here velocity at the starting point is very less, and as height is increasing, velocity is also increasing. At a specific height in between 0.48 and 0.49 meter, velocity is maximum. It is in the range of 1.09 meter per second, and again after that location velocity is falling, right? So at 0.5 meter velocity is 0 again. This is the velocity distribution through this mold cavity. Next one we'll see temperature of solid. You see initially temperature was 20 degrees centigrade, and after temperature 74.14 degrees centigrade. We can see pressure distribution also, and initially pressure at the inlet was very less. When the height is 0.45 meter, pressure is less, and at the exit point when the height is 0.5 meter, in that location pressure is 101,542 pascal. Pressure is also increasing. Excluding that, you can see mass fraction of liquid aluminum also. Mass fraction of aluminum at defined height, it is different, right? Let's close it. Next to that, we're going to see something else like XY plot through this inclined line, right? So let us close it, and we're going to see again XY plot through the different line, inclined line. Insert XY plot, and let us select that inclined line from here, and we'll see pressure and temperature of fluid. Last case we saw temperature of solid. Now let us see temperature of fluid through the inclined line, and you can export this one to Excel again. First one is temperature of fluid. You can see here initially temperature of fluid, as length was increasing, it was constant, and after that we can see a steep rise, and finally the temperature is 571.42 degrees centigrade, right? Next one is pressure. Initially pressure was very less, and at the end of this simulation you can see pressure is very high. It is in the range of 101,584.98 pascal, right? Let us close it. Now finally we'll see our goal plots. In our goal plots we want to see temperature distribution through different conical surfaces. Let us see that. So goal plots, insert goal plots, and we are bothered about temperature of fluid at inner and outer conical surface. Let us select both the goals, and we can export to Excel. Let us view it from here. First one is temperature of fluid at the inner surface. It is showing that after 1525 numbers of iterations, temperature at the inner conical surface is 346.1 degrees centigrade, and similarly for the outer conical surface it is also exactly same. It is 346.1 degrees centigrade. That is, at both the inner and outer conical surface, average temperature of fluid is almost equal. It is 348.65 degrees centigrade, right? Let us close it. With this one we'll conclude our today's analysis. It is a very simple analysis of molding process, and through this molding process we have seen temperature and pressure distribution at different locations of this mold cavity, right? So thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.